In this video, we'll look at one application that requires use of the chain rule. So here's a function from an environmental study that indicates that the average daily level, capital P, of a certain pollutant in the air in parts per million can be modeled by this function, P of n equals 0.25 times the square root of 0.5n squared plus 5n plus 25, where n represents the number of residents in the community in thousands. So this question asks, at what rate is the level of pollutant increasing when the population of the community is 12,000? And then we would like to interpret our results. So whenever we are considering a rate of change, anything changing over time, especially an instantaneous rate of change, or in rate of change at one single value, in other words, in this case, at 12,000 exactly, that is found by finding a derivative. So in this example, right, when we see the word at what rate, that is, again, a key giveaway that we're looking for derivative. Huge idea in this class that the derivative of a function means its rate of change, in particular its instantaneous rate of change. So what we're going to need to do is differentiate this function. Okay, so it might be a good idea to first start, before we differentiate, by rewriting this without a square root and with a 1/2 power instead. Now what we have here is a constant multiple with the 0.25 multiplied by something that is more than just a function of, in this case, n, or more than just n. It's a function of n raised to a power. So here in this whole thing, it looks like what we have here, if we were going to look at the general structure, is 0.25b to the 1/2 power, where b is 0.5n squared plus 5n plus 25, and b prime, the derivative of that, will be 1n plus 5. Now, if we're going to differentiate something of this form, 0.25 b to the 1/2, this is going to look like 0.25 times 1/2, right, by bringing the 1/2 down and multiplying. So that will give us half of 0.25, so that's 0.125, b to the negative 1/2. And then we have to multiply by the derivative of the base, or the derivative of the inside function. So if we're going to differentiate this whole thing, it's going to look like, okay, bring the 1/2 down, multiply by the 0.25. So there's the 0.125. Then we leave the base the same and subtract 1 from the power. So this looks like 0.5n squared plus 5n plus 25 raised to the negative 1/2. Then we have to multiply all of this by the derivative of the inside, or b prime, right? And that is in parentheses all of n plus 5. Okay, so what we have here, right here, is the 0.125 b to the negative 1/2. And then here is the derivative of the inside, or b prime. Now we want to simplify this always. Simplified derivatives are best to work with. So it looks like we have, in this example, remember we want to take our number out in the front and our b prime, and oftentimes combine them together. That is really mostly true when the b prime is a single term. Here our b prime has more than one term to it. It's n plus 5. But we can still kind of put them together. So I would just recommend writing this as like 0.125 times n plus 5. And then we've got times 0.5n squared plus 5n plus 25, all raised to the negative 1/2 power. Now the negative exponent, we don't want to leave that in our answer because it is hard to work with and hard to think about. So we can bring this whole thing down to the denominator, change this whole first piece, instead of multiply, it'll be divide, and we'll make the exponent on the 0.5n squared plus 5n plus 25 a positive 1/2. So that's going to look like 0.125 times n plus 5 divided by 0.5n squared plus 5n plus 25, all raised to the 1/2 power. Another way that we could write that, if we wanted to, is by rewriting that denominator as a square root. So we could write that as 0.25 times n plus 5 over the square root of 0.5n squared plus 5n plus 25. So here is a function that gives us the rate of change of the pollution with respect to the population. We want to know the rate of change of the pollution when the population is 12,000 people. So because the population is already measured in thousands, we don't want to plug in 12,000, we just want to plug in 12. Okay, so units, when you're like working with a function, it's important to keep track of. Sometimes things are measured in thousands or millions, just so that the coefficients on the function tend to be smaller and easier to work with, and your model tends to be more accurate as well. When you start plugging in really large numbers, things can just get a little wonky. So we want the rate of change when the population is 12,000. So again, that means that n is equal to 12. So we'll plug in 12 in for n into capital P prime. Okay, so it'll just be 0.125 times 12 plus 5, all divided by square root of 0.5 times 12 squared plus 5 times 12 plus 25. And so carefully take out your calculator and carefully plug this in. I might recommend doing the numerator first, hitting enter, figuring out what that is, doing the denominator second, hitting enter, figuring out what that is, and then doing the whole divided part after. There's a lot to put in here into one step in a calculator. If you do this, I believe that you should get 0.17. So it's one thing to get a number, numerical answer in math. That's great to be able to do. But we also want to be able to do a little more than just what a computer could do, and we want to interpret this. So rates of change always have units. Any function that models a real life situation always will have units, like a meaning. So this is the rate of change of the pollution. We just scroll up. Right, the measure of just P of n is in parts per million. And the input n is residents in thousands. So the rate of change units are always the measure of the output over the measure of the input. It's just like slope. Change in y over change in x. The units become the same thing. Change in y units over x units. So output units over input units. So this is the change in pollution in parts per million per change units of the input, which is thousands of people. Now this can be a little deceiving. So it says 0.17 parts per million per 1,000 people. But this isn't for any 1,000 people. It's just for the 1,000 around where we plugged in, which was 12 or 12,000. If we plugged in a different number, 13, 14, 6, we would get a different rate of change. So what this means, and it's important to be able to interpret this and understand the meaning of this per 1,000 people here in this case, or this rate of change in general. So this means that if the population or the number of people in the community increased by 1,000 people, so from 12,000 to 13,000. So it's not, again, not just any 1,000, it's the 1,000 from where we plugged in. Then this would be the approximate rate of change of the pollution. So the pollution would, in this case, increase because the rate of change is positive. And the amount of increase would be approximately 0.17 parts per million. So starting at 12,000, adding an additional 1,000 people to this community would, according to this model, increase the pollution level by about 0.17 parts per million. Okay, so that is the end of our chain rule introduction. We will be using derivative rules throughout the rest of the semester. So I really encourage you to take the time to practice these. Make sure that you have them down so that when we start adding to them, it won't be as difficult trying to learn more than one thing at once in the future. So in the next section, 2.6, we will learn about higher order derivatives. So we'll do a little more physics application and also review all of our rules in the process. So I'll see you then, and I hope you have a great day.